So, last class I was discussing the another method to determine or to check the stability of oil, and that method was the ultimate soil reaction method. And then I have discussed the load factor and the load combinations, and then I was discussing about the normal force which is acting along this rupture surface, because it is assumed that because of the rotation of that oil along a point say O. So, this is the point along which this oil is rotating. So, there will be a rupture surface below within the soil below the oil, and the normal force, total normal force along that rupture surface is W R W by B theta plus sin theta cos theta. Okay. So, now if I look at this figure, that sin theta will be equal to, so because this is theta, this is N D, this is R and this one is B. So, this will be definitely B by 2. So, sin theta will be B by 2 divided by R. So, sin theta will be B by 2 R. B by 2 is this value, this is theta, this is the R. So, this will be B by 2 divided by R, because this in this triangle we can get that. Similarly, cos theta will be equal to, this is N D. So, this will be N D divided by R. So, the tan theta will be equal to sin by cos. So, that will be B by 2 N D. And R value, what is R? Because we have to now convert all these parameters. So, this is R. R will be nothing but root over B by 2 square plus N D square, because this is R. So, this is B by 2 square plus N D square and root. So, we can write that this is equal to root over B square plus 4 N square D square divided by 4. So, finally, I can write this is equal to B by 2 root over B by 2, if I take outside, 1 plus 4 N square D square divided by B square. So, this is the equation of R. Now, if I put all these values in the Fn, the R, theta, sin theta. So, theta I can write that theta is equal to tan inverse B by 2 N D. So, theta I can write. So, I can put all these values here, and finally, I will get the expression of Fn. So, that will be W by 2, then there is a W by 2, then R is there. So, if I put this all theta, sin theta, cos theta value and R value in terms of N D and B, then I will get and simplify the equation, then I will get the Fn expression is like this. So, W by B root over 1 plus 4 N square D square divided by B square, because this is R, and then theta is tan inverse B by 2 N D, and if I multiply sin theta and the cos theta, if I multiply sin theta and the cos theta, then also I will get the term 2 N B D divided by B square plus 4 N square D square. Okay, so, this is the expression. So, this B will cancel out, in the R term is there is a B. So, this will be simple W by 2 and this term. So, and then if I put theta and cos theta and sin theta, then I will get this equation. So, this is the Fn. So, now Fn is acting along this surface. Now, what will be the moment due to this Fn? Okay. So, Fn is acting Fn into tan phi is acting around the surface. So, the moment due to this Fn tan phi, because now Fn is the normal, and if I multiply with that Fn with tan phi, then that will give you the shear stress which is acting along the rupture surface. Now, the moment due to the shear stress will be how much? So, moment due to the shear stress along the rupture surface along this rupture surface will be how much? Fn tan phi into r, r is the radius, and that radius is same for along the rupture surface. So, that will be the moment. So, this moment mb, that will be Fn tan phi into r. Now, it is assumed that Nd is equal to 0.2 d. So, it is observed that this point of rotation is around 0.2 d. Okay. So, that above the base of the well. So, that means it is assumed that Nd is equal to 0.2 d. So, it is recommended by observation, it is recommended that the point of rotation is 0.2 times of d above the base of the well. So, this is the point of rotation. Here this is the point of rotation. Okay. So, now I can put this value here, and then I will get the mb. So, mb is Fn tan phi r. Now, r also I can put this value, which is also in terms of Nd and b. So, now if I in place of Nd, if I put 0.2 d, and then I simplify this equation. So, and I will put Fn here, tan phi also I can replace by this equation. So, sorry, tan phi is the friction angle. So, tan phi should be there. So, tan phi will be there. I can replace, r I can replace with this equation. Okay. So, r I can replace with this equation. Then Fn I can put with this equation, and with this equation I can put 0.2 d in place of Nd, and then if I simplify that, then I will get the mb will be q wb tan phi. Now, where q is a constant, depending on the shape of well, because and d by b ratio. Okay. So, for different, that means this q is also determined from this equation, and for different d by b, because in this equation now this mb equation, what are the terms are present? Only the d b, because Nd is replaced by d. So, there will be only d and b. Okay. So, that means, and there is a w term also. So, w, b and d. So, this q is basically function of d by b and the shape of the well. So, and then these q values are given in terms of d by b value. So, if d by b value, and this is the q value. So, if d by b is 0.5, q is 0.41. If d by b is 1, q is 0.45. and d by b is 1.5, q is 0.5. Is d by b is 2, q is 0.56. If d by b is 2.5, q is 0.64. And these values are for square or rectangular weld. Now, note if it is a circular well, for circular well we have to multiply by a shape factor of 0.6. So, that means, first we for circular well we will get the q value from this table, and then we have to multiply by 0.6 with this value, with these values. Okay. For these values we can directly use for square and rectangular well base, but for circular well we have to multiply by 0.6 with these values. Okay. So, this is MB we can determine from this equation. So, that means MB now we can determine. So, this is the MB, which is the moment due to the shear stress acting along the rupture surface. So, this MB we can determine. Next is that suppose this is the well position, and again this well is rotating with a point. So, there one side will be active, one side will be passive, and I have discussed that what will be the pressure distribution, because it is not acting at the base, because if it is acting at the rotating at the base, then one side will be totally passive and another side will be totally active, because in elastic theory analysis, so that is the case, because one side is totally active, one side is totally passive. But for Tarzaki's analysis, this point of rotation for light well is slightly above the base of the well. So, that means one side will be active and then another side will be active, and that thing will change above the point of rotation and below the point of rotation. So, here also the point of rotation is above the base of the well. Okay. So, that means here also the active passive zone will change based on the point of rotation. If above the point of rotation and below the point of rotation, the active passive zone will change. So, but in the Tarzaki's analysis I have shown how we can get the net pressure distribution in such case, but here this pressure distribution is assumed. So, that assumed pressure distribution is that again. So, if I draw that net pressure distribution. So, again there will be one side is active, one side will be passive. So, there will be a net pressure distribution. So, that is the net pressure distribution. Okay. So, this is net pressure distribution, and this is equal to Kp minus Ka gamma dash, and we can say this is d. Okay. Because this is the depth of the well, and this is also Kp minus Ka into gamma dash d. Okay. So, this is also depth of the well. But here the net pressure distribution is drawn or assumed in such a way that this is say point of rotation. Okay. So, O. So, this is a point of rotation. So, that point of rotation is assumed at a distance of 0.2 d from the base. Now, the pressure distribution is assumed is such that, so at point of rotation the net pressure is 0. So, this will be the net pressure distribution of the well. So, this is the net pressure distribution for the or assumed pressure distribution for the well, and obviously if the horizontal force is acting in this direction, then only this will be the horizontal force is acting in the other direction. So, because the horizontal force can be at any direction. So, this figure I have drawn, this is acting from left to right, but it can be from right to left. So, it is not a problem. So, but according to that I have to draw the pressure distribution. So, here the pressure distribution I have drawn in this direction means the horizontal load is acting in the other direction. Okay. So, but you can draw it in the other side also if the direction of the horizontal force is different. So, that is not a issue. So, for this particular case, so definitely the horizontal force is acting in this direction, but this can be other direction also, then this figure will be totally the opposite. This side will be that means this figure will just shift. So, this is the scour level. So, this is so now this is point D, point 2D, and this value is say D1 and this is total D. So, now if I write this is A, this one B, this one C, then this is D, and then if I draw one line here. So, this is say E and this is F. Okay, or if I write this point is E, this point, and this point is F, and this is the center line of the well, this is the width, and definitely this will be B by 2, this will be B by 2. Fine. Now, from this particular case, if I consider triangle DEF and triangle OBD. So, we are considering DEF this triangle and DOB this triangle, and if I take this distance is y, or this pressure, this value is y and this value is x, say this is x and this one is y. Then from the similar triangle, because these two triangles we have to consider, this is a similar triangle, one is this bigger one, another is the smaller one. So, this similar triangle, that means this bigger one and this smaller one. This similar triangle I can write that d1 divided by x plus y. So, that will be equal to this height is 0.2d. So, this is 0.2d divided by x. So, now if I simplify this equation, so I can write after simplification this equation, I can write d by x will be equal to 5, because 0.2 means 1 by 5. So, 5 d1 minus d divided by y. So, this is equation number 1. Now, again from another similar triangle ACB and the similar triangle CEF, ACB and then CEF. So, this bigger triangle ACB and this smaller triangle CEF. So, from these two similar triangle also I can write that d by this is also x, this is x. So, that will be this distance, then if this is x, this one y. So, this will be definitely x minus y. So, that will be d1, because this height is d1 and this distance will be x minus y. So, this will be x minus y. and then if I simplify this equation, so then it will be d by x is equal to d minus dy divided by y. So, now if I compare equation number 1 and 2, then I can write that from equation 1 and 2, we can write that 5 d1 by minus dy is equal to d minus dy y. Okay? And this y will cancel out. So, if I simplify this equation, then I will get that 5 dy minus d will be equal to d minus dy. Thus, d1 is equal to d by 3. So, 5 d1 minus d will be equal to d minus d1, then d1 will be equal to d by 3. So, this d1, the point where it is changing the stress from this side to that side, this E point is at a it is d by 3 distance above the base of wall. So, now we have determined what is the value of d1 in terms of d. So, now we have to take the moment. So, what are the moments we will consider? So, first we will consider that the moment ms. So, this ms is due to soil reaction or resistance. So, ms soil resistance moment due to the soil resistance or soil resistance moment. So, this soil resistance moment we are taking with respect to O, because this is the point of rotation. So, this is the point of rotation. So, we are taking the moment with respect to O, that is point of rotation. So, we are taking the moment with respect to O. Now, if I take the moment with respect to O, then what are the moments? So, this moment above the point O and moment due to the soil resistance below the point O, so both will act in the same direction. So, we have to add them, okay? And then we have divided into 3 parts. This is the part 1, okay? This is part 2, this 3 triangle. So, this is the triangle 1, then this there is the another triangle that we have considered, okay? So, this is the triangle 2, and this is the triangle 3. So, we have taken 3 triangles. Okay. Now, I will take the moment for this soil resistance with respect to O. So, now if I take the moment, then the force will be for the triangle 1 half. Now, if this is d1 is equal to 1/3 of d, then this point, this value will be 2/3 of d, and this point, this distance will be equal to, because this is 0.3, this one is 1/3 of d means 0.33 d. So, this is 1/3 of d, or d1 is equal to, I should write that d1 is equal to 1/3 of d, which is nothing but 0.33 d. So, this is 0.2 d. So, this will be 0.13 d. Okay. So, this should be 0.13 d, because this is 1.33 d. So, now for the first triangle, triangle 1, the total force will be half into 2/3 of and then the net pressure, because this net pressure at this point E point will be definitely 2/3 gamma dash d Kp minus Ka. Okay, because if this is at a depth of d, if this is Kp minus Ka gamma dash d, then at 2/3 of d, this will be Kp minus K gamma dash 2/3 of d, because that is the point which is at 2/3 of d from the top, because at d it is Kp minus K gamma dash d. So, at 2/3 of d you have to replace d by 2/3 of d, that I have done. So, this is the pressure distribution at this point. So, I can say the moment Ms at this point, the force for the triangle 1 will be then 2/3 of gamma dash d Kp minus K into 2/3 of d. So, that is the force. Then lever arm will be, because we are taking moment, lever arm will be, then we are taking from point O. So, lever arm will be 0.13 d plus 0.13 d plus 1/3 of 2/3 of d. Okay. So, that we can write here that lever arm is 0.13 d plus 1/3 of 2/3 d. So, this is for triangle 1. Now, for the triangle 2, this small triangle, the area base is 0.13 d, height is 2/3 gamma dash d Kp minus K. So, I can write this point, small triangle is half 2/3 of gamma dash d Kp minus Ka into 0.13 d, then the lever arm will be 0.13 d into, this is from here. So, 2/3 of 0.13 d. So, this will be 2/3 of 2/3 of 0.13 d. Okay. So, this is the force and lever arm is 2/3 of 0.13 d. Okay. And when we are talking about this moment, so if I look at this force, so these forces will be this is kilonewton per meter cube and 2d you are multiplied. So, this will be kilonewton per meter. So, these forces is kilonewton per meter. Okay. So, now if I want to convert them in kilonewton, that means this force is kilonewton per meter. So, if I convert them in kilonewton, you have to multiply with that L, because this is the L. So, that long distance. So, side of the wall. So, this is the side of the well, and this forces is kilonewton per meter. So, you have to multiply with L. So, that is why we will multiply with L. Okay. So, here also we will multiply with L. Clear? Now, it is kilonewton per meter. Now, for the third triangle, the force will be half into gamma dash d Kp minus Ka, then the height is 1/3 of, so this height is 0.2 d, this height for the third triangle is 0.2 d, this is the base. So, this will be 0.2 d, and then the lever arm will be from here, the lever arm will be 2/3 of 0.2 d. So, lever arm will be 2/3 of 0.2 d. So, if I simplify this equation, then it will come roughly, it will come 0.096 gamma d cube L Kp minus Ka. Oh, again we have to multiply one L here. Okay. So, which is roughly taken as, so Ms is taken as 0.1 gamma dash d cube L Kp minus Ka. Okay. So, Mb we have calculated, ms also we have calculated. Now, next one is the friction resistance moment. Which is mf. So, what is friction resistance moment? That means there will be a soil reaction. So, there will be a soil reaction. Because of this soil reaction, there will be a friction force will generate along the side of the well. So, because of that friction, how much will be the moment? So, that means that we have to calculate. So, to calculate that, so what is the total amount of force which is acting? Now, for that purpose, the total force per meter will be equal to, now we have these two triangle. Okay. We have taken the three triangles, but now for this calculation purpose, we are taking two triangles, this the bigger one and one triangle above the point O and one triangle below the point O. So, that two triangle reaction is giving the total soil reaction. So, that total force will be equal to, for the upper triangle, that force is, for the lower triangle first we are calculating. So, for the lower triangle, half into gamma dash d Kp minus Ka into 0.2 d. So, that is for the lower triangle, this is Kp minus Ka gamma dash d into 0.2 d half, and for the upper triangle, this is the total base and this is the height. So, total base will be, for the upper triangle, this is half into 0.8 d. Why 0.8 d? Because this is 0.2 d. So, that means this total one will be 0.8 d. Okay? Or the total one will be 0.8 d. Or I should write this is, because this from base to point 1 is 0.2 d. So, from A to O, from top to point O will be 0.8 d. From base B to O is 0.2 d. So, point A to O is 0.8 d. Okay. So, I can write that this is 0.8 d and then the height will be 2/3 gamma dash d Kp minus K. Okay. Now, if I simplify this equation, then this will be 1.1 divided by 3 gamma dash d square Kp minus Ka. So, the total friction force so this was per meter. So, this will be, you have to multiply by L. So, this is 1.1 divided by 3 gamma dash d square Kp minus Ka, this is into L. Now, one thing I want to mention, that as I have already discussed, that this is these Kp and Ka, these Kp or Ka and Kp are as per Coulomb's, as per the Coulomb's theory. Okay. So, again there will be a component Coulomb's theory. So, that means P is acting, or P net is acting at a delta, and friction angle, horizontal force was acting with a value of P net into cos delta, but the friction force, so that is acting, this friction force that will act with a value of P net sin delta. So, because this moment is due to the friction that is acting along the side length of the well. So, that means we have to multiply with a sine delta. Now, here delta is taken as 2/3 of phi, but delta should not be greater than 22.5 degree. So, it will take 2/3 of phi, or it should not be greater than 22.5 degree. So, we can write that so we can write here that MF will be equal to 1.13, and then this is 1.1 divided by 3 gamma dash d square Kp minus Ka into sine delta. So, this is the force, this is total frictional force. So, the moment will be into sine delta into L into this is the force, this is 1.1 by 3 gamma dash d square Kp minus K sine delta L is the force into B by 2, because this is acting at the side, because this is the where this force is acting, okay, friction force. Okay. Frictional force is acting. So, and moment we are taking from this point, okay. Okay, this moment we are taking from the center. So, we have to multiply with the B by 2, that is the lever arm. So, it will be B by 2. So, finally, the MF will be equal to 0.183 gamma dash Kp minus Ka L B d square sine delta. So, this equation is for rectangular footing. So, in the next class I will discuss that how I will get these equation of MF for the circular footing, circular well. So, this is for the rectangular well, and the next class I will discuss the circular well, and then how I will set the condition that this moment, summation of this moment, because these are the resisting moment, okay, should not be less than the moment which is applied. So, those things will be discussed in next class. Thank you.